All right, let's put all of our tests together and analyze the function f of x is equal to x plus 3 divided by x. We're going to put all of our information together to see if we can sketch a graph of this function. Let's do it. First, let's find the x-intercepts and let's find the y-intercepts. An x-intercept is whenever y is equal to 0. So we have 0 equals x plus 3 over x. And we need to solve that equation to find the x-intercepts. To do that, let's multiply the entire equation by x. We get 0 is equal to x squared plus 3. Would you agree with that? If I just multiplied this entire thing by x, we'd get 0 equals x squared plus 3. And notice that that's not going to have any real solutions. There's no number I can plug in here that that'll be squared and becomes positive, and then add something to it. That'll never equal 0. So that tells me we have no x-intercepts. The y-intercept is when we plug in a 0 for x, and when we do that, we get 3 divided by 0, so we can't do that, so that's going to mean we have no y-intercepts. So the fact that we have no intercepts gives us a clue as to where our asymptotes are going to be. Remember that for vertical asymptotes, the vertical asymptote occurs whenever we have a 0 in the denominator of a fraction, which we already figured out happens when x is equal to 0. So x equals 0 is going to be our vertical asymptote. Do we have a horizontal asymptote? Well, this is kind of tricky, and you kind of have to do a couple examples of this to understand what's happening. But basically, a horizontal asymptote or a slant asymptote is what happens at the end behavior of our function. So let's take a look at what's happening. I have x plus 3 divided by x. Okay, the question you want to ask yourself is, what happens when x gets really, really big? And the answer is, as x gets really, really big, watch what happens to this term. If x gets really, really big, what happens to 3 divided by x? Well, x gets really, really big, so I have 3 divided by a really big number, which means that this will get smaller and smaller and smaller. In fact, it will start to approach 0 as x goes to infinity. So what that means is I have x plus a number that's getting really, really tiny. That means that as x gets really big, the function becomes f of x equals x. Or at least it will always approach this major term right here. And again, the reason is because this piece is getting smaller and smaller and smaller as x gets bigger. And so there's actually no horizontal asymptote, but there is the slant asymptote of y equals x. That's what this function approaches as x gets big. And I know that's not a great explanation. You kind of just have to do this a couple of times to start to understand what the function will look like as x gets big. All right, so to start our graph, we know we have a vertical asymptote here at x equals 0, and we know at the end of the graph we're going to have a slant asymptote. All right, what are our relative extrema? Okay, well, we can do that by taking the first derivative. So f prime of x will equal 1 plus, because the derivative of x is 1, plus the derivative of 3 over x is negative 3 over x squared. So if you don't remember that, check your homework or check previous videos, but the derivative of 3 over x would be negative 3 over x squared. To solve this, we need to set this equal to 0. So I get 0 is equal to 1 minus 3 over x squared, times that all by x squared. By the way, I'm going to put a box around our first derivative because we'll use it later. Times everything by x squared, and we get 0 is equal to x squared minus 3, which means that when I add the 3 over, I get x squared equals 3, which means that x is equal to positive or negative square root of 3. So at positive negative square root of 3, we're going to have a relative maximum or a relative minimum. Okay, that's good to know. Next, we need to know, where is our function increasing or decreasing? Well, in order to do that, here I have negative square root of 3. Here I have square root of 3. And we just need to test one point in each 3 of these sections to see when we're increasing and where we're decreasing. So let's plug in, I can't plug in 0 because that's undefined. So let's plug in 1 and see what happens. If I plug in a 1, I get 1 plus negative 3 over 1, which is negative 2. So that means we're decreasing right here because I get a negative. I get negative 2 when I plug 1 into the first derivative. So we're decreasing in between negative 3 and 3. Okay. In fact, actually, now that I think about it, we really need to be testing, because I have an asymptote at 0, we need to test all 4 of these sections. So let's be careful with this. We actually need to test all 4 of the sections if we have an asymptote, because that's a discontinuity. So, okay, so what was the point I just tested? We just tested 1, so that means we're negative right here. Let's plug in negative 1. If I plug in negative 1, I get negative 1 squared, which is 1 again. So I get 1 minus 3 again. So it turns out that will be decreasing in both of those places around the asymptote. Okay? We are going to be increasing wherever the derivative is positive. Let's plug in a really big number like, let's plug in let's plug in 2. Because that would be the square root of 4. So let's plug in 2. I get 2 squared is 4. So I get 1 minus 3/4, which is going to be a positive number. Or if I plug in 100, I get 1 minus 3 over 100 squared. That's going to be a really tiny number. So 1 minus that will be positive. So if I plug in any large number for x, I get 1 minus a fraction, which will be positive. Likewise, if I plug in a big negative number, because it's being squared, it turns positive. So if I plug in negative 100, I get 1 minus 3 over negative 100 squared. Again, that's just 1 minus a tiny fraction, which will be positive. So we're increasing and then decreasing, decreasing and then increasing. So we're increasing from negative infinity to negative root 3. And notice I'm using open intervals. And we are increasing from square root of 3 to infinity. We're decreasing from negative square root of 3 to 0, but not including 0, and we're decreasing from 0 to square root of 3. So I need to go ahead and do 2 intervals for that. Okay, let's see if we have any inflection points. To do that, I need to take the second derivative. Second derivative of this, the 1 goes away. So I need to take the derivative of negative 3 over x squared. We'll take the derivative of that. So that's going to be the derivative of negative 3x to the negative 2. So that's going to be positive 6x to the negative 3, or positive 6 over x to the 3. That's our second derivative, and if you need help on that, check back on the videos where we do the second derivative. Okay, 6 over x cubed is our second derivative. This will never equal 0 because there's no number I can plug in for x down here that'll make the whole thing be 0. So that means we have no inflection points. Let's do one last thing. Let's find out where we're concave up and concave down. And I know I'm going a little quickly. If you're lost, just feel free to rewatch parts of this. We're concave up when the second derivative is positive, and concave down when the second derivative is negative. So notice that if I plug in a positive value for x, it'll be positive. So that tells me that we're concave up from 0 to infinity, because whenever x is positive, the second derivative is positive, which means we're concave up. Likewise, if I plug a negative into x, it'll be negative cubed, which is negative. So if I plug in a negative for x, we get a negative for the second derivative, which means that we're concave down. So we're concave down from negative infinity to 0. Okie dokie. That's it. So, by the way, that's not to be confused with where we're trying to test a max or a relative max or min. If the second derivative is positive, we're concave up. If the second derivative is negative, we're concave down. If the second derivative is 0, then that means it's an inflection point. If you put all of this together, you should get the following graph. You might want to plug in a couple points to see what happens, like plug in 1, and you see we get 1 plus 3 over 1, which is 4. So there's a point on our graph. If we plug in -1, we get -1 plus 3 over -1, which would be -4. Okay, now we know that we have maximums and minimums at the square root of 3 because we found those points. So notice here we went from positive to negative, so that means we have a positive to negative, so that means the square root of 3, which is about right here, will be a maximum, and so this happens. This right here is the negative square root of 3. We have a little maximum right here, so this point would be a little lower, and then notice at the end behavior I approach the slant asymptote. Likewise, at the positive square root of 3, we're going to have a minimum, because here we went from negative to positive, which means our slope went from negative to positive, and so this happens. And so you can see how without using a graphing calculator, I can get a pretty good analysis of what the actual function looks like by using the first and the second derivatives. We put it all together. We put the intercepts together, the asymptotes, first derivative to figure out where it's increasing and decreasing, second derivative to see where it's concave down and concave up. This honestly just takes practice. It takes a little bit of practice to do this, doing several different types of equations, but I promise that with time you will get the hang of it. In the next video, we'll do another example.